The information provided in this video is for educational and entertainment purposes only and does not constitute professional, legal, mechanical, or financial advice. The operation of transport vehicles and the management of logistics entities are subject to complex federal, state, and local regulations, including those set forth by the Department of Transportation and the Federal Motor Carrier Safety Administration. Viewers are strongly encouraged to conduct their own due diligence and consult with qualified professionals before making any decisions related to the transportation industry, vehicle acquisition, or commercial operations. Imagine for a moment that every single wheel in the United States suddenly stopped turning. Within the first 24 hours, the sophisticated just-in-time delivery systems that power our modern life would begin to fracture. By the second day, your local grocery store would be stripped of fresh produce and dairy. By the third day, the very water coming out of your tap could become a health hazard because the chemical treatments required for purification can no longer be delivered. This is not the plot of a dystopian film. It is the physical reality of the American economy. We are a nation built on movement, yet most people cannot accurately define the very machines that keep us alive. Most people look at a vehicle and see a car, a truck, or a bus. But when we look through the lens of logistics and infrastructure, we are seeing something much more specific: a transport vehicle. The difference between a standard car and a transport vehicle is the difference between a hobby and a lifeline. In this deep dive masterclass, we are going to deconstruct the invisible giant that supports 330 million people. We are going to look at why a delivery van is legally distinct from your SUV, how the weight of a single axle can change the course of interstate commerce, and why understanding these machines is the key to understanding the American way of life in 2026. This is the ultimate guide to the backbone of the United States. To understand what a transport vehicle truly is, we must first strip away the paint and the chrome and look at the fundamental purpose. At its core, a transport vehicle is a specialized machine designed for the displacement of mass across distance for the purpose of utility. While your personal sedan is designed for the comfort and movement of individuals, a transport vehicle is designed for the efficient relocation of goods, bulk materials, or large groups of people. In the United States, this distinction is not just semantic, it is a matter of federal law and economic classification. The Department of Transportation, or DOT, looks at vehicles through a specific set of criteria that determines how they are taxed, where they can drive, and who is allowed to operate them. The first pillar of our deep dive is the Gross Vehicle Weight Rating, or GVWR. This is the metric that separates the amateurs from the professionals. In the United States, the FHWA, which is the Federal Highway Administration, categorizes vehicles into 8 distinct classes based on this weight. Class 1 encompasses your standard pickups and minivans, typically weighing under 6,000 pounds. However, as we move into Class 3 and above, we enter the realm of true transport vehicles. When a vehicle exceeds 10,000 pounds, it enters a new world of regulatory scrutiny. This is where we find the box trucks that deliver your furniture and the heavy-duty vocational vehicles that maintain our power lines. But why does weight matter so much? It comes down to the physics of our infrastructure. A standard passenger car exerts a relatively negligible amount of stress on the asphalt. However, a fully loaded Class 8 tractor-trailer, which can weigh up to 80,000 pounds under standard federal limits, exerts as much wear and tear on a highway as thousands of passenger cars combined. Historical trends in American engineering show that our entire interstate system, envisioned by Eisenhower, was designed specifically to accommodate these heavy transport vehicles. Without them, the massive geographical expanse of the United States would be an insurmountable barrier to trade. Let us look at a case study of the modern American supply chain to see these vehicles in action. Consider a single gallon of milk in a supermarket in Ohio. To get there, it required a sequence of at least 4 different types of transport vehicles. First, a specialized collection truck, often a tanker made of food-grade stainless steel, had to move the raw product from the farm to the processing plant. This vehicle is a transport vehicle because it is designed with a specific utility in mind, maintaining temperature and hygiene while moving liquid mass. Second, after processing, the milk is loaded into a refrigerated trailer, known in the industry as a reefer. This is a masterclass in transport engineering, featuring an independent diesel-powered cooling unit that must maintain a constant 34 to 36 degrees Fahrenheit, regardless of whether the truck is driving through the heat of a Georgia summer or the plains of Kansas. The third vehicle in this chain is often the last-mile delivery van. In 2026, we have seen a massive shift in this category. These are the vehicles you see in your neighborhood every day. They are optimized for high-frequency egress, meaning the driver can get in and out hundreds of times a day without physical strain. They are designed with low floors and sliding doors, features you won't find on a vehicle meant for a Sunday drive. Finally, we must acknowledge the vocational transport vehicles that support the entire process, the fuel tankers that keep the fleet running, and the maintenance trucks that repair the roads. When we talk about transport vehicles, we also have to talk about the concept of payload versus tare weight. Tare weight is the weight of the vehicle when it is completely empty. Payload is the weight of the cargo it can legally carry. A true transport vehicle is engineered to maximize payload while minimizing tare weight. This is why you see so much aluminum and high-strength composite material in modern trailers. Every pound saved on the vehicle's frame is an extra pound of revenue-generating cargo that can be hauled. This is the fundamental math of the American logistics industry. If a company can increase its payload by just 5% across a fleet of 1,000 trucks, the potential outcomes for their bottom line are staggering. This efficiency is what allows the United States to have some of the lowest logistics costs as a percentage of GDP in the developed world. Furthermore, we must address the human-machine interface of the transport vehicle. Unlike a passenger car, where the interior is designed for entertainment and aesthetics, the cab of a commercial transport vehicle is a high-stakes office. In 2026, these cabs are equipped with electronic logging devices, or ELDs, which are mandated by federal law to track every second of the driver's duty status. They feature telematics systems that broadcast the vehicle's location, fuel consumption, and even tire pressure to a central dispatch center in real time. The vehicle is no longer just a machine. It is a data node in a global network. As we progress through this series, we will examine the different modes of transport vehicles, from the massive 777 freighters that dominate our skies to the intermodal chassis that move containers from the port of Long Beach to the rail yards of Chicago. But for today, the most important takeaway is this: a transport vehicle is defined by its mission. If a vehicle exists to facilitate the movement of the economy, it is a transport vehicle. Whether it is a bicycle used by a courier in Manhattan or a massive mining truck in Nevada that stands 3 stories tall, these machines are the red blood cells of our national body. They carry the nutrients, the food, the fuel, and the fiber that allow our society to function. By the time we finish this 10-part masterclass, you will never look at a truck on the highway the same way again. You won't just see a vehicle. You will see a complex, regulated, and vital piece of engineering that is the only thing standing between civilization and total logistical collapse. We are just getting started on this journey into the world of heavy metal and high-stakes movement. To truly grasp the magnitude of transport vehicles in the United States, we have to look at the Federal Bridge gross weight formula. Imagine Alex, a fleet manager in 2026 based out of a logistics hub in Indianapolis. Alex doesn't just look at a truck and see a vehicle. He sees a complex equation of weight distribution. Most Americans assume that the weight limit for a semi-truck is a flat number, but in reality, it is a dance between the number of axles and the distance between them. The reason you see those massive heavy-duty trucks with extra wheels that can be raised or lowered, known as lift axles, is strictly due to the physics of infrastructure protection. If Alex loads 80,000 pounds onto a short trailer, he risks snapping a bridge or pulverizing the asphalt. By spreading that weight across more axles and a longer distance, the pressure per square inch on the road surface drops, allowing the vehicle to pass legal scrutiny. This is the first rule of transport vehicles. They are designed to balance the maximum possible payload with the physical limits of the American soil. In the 2026 landscape, the classification system remains the bedrock of how we define these machines. We categorize them from Class 1 to Class 8, and the jump between them is massive. A Class 1 vehicle is your typical light-duty truck, like a Ford F-150 or a Chevrolet Silverado, which you might use to haul a boat or some plywood from a home improvement store. But as we move into Class 6, we encounter the medium-duty workhorses. These are the school buses that carry the next generation to class and the beverage trucks that restock your local convenience store. When you hit Class 7 and Class 8, you are dealing with the heavy hitters. These are the tractors pulling 48 or 53-foot trailers. A Class 8 vehicle is defined as any transport vehicle with a gross vehicle weight rating exceeding 33,000 pounds. Historical trends show that these Class 8 vehicles, while making up a small percentage of total vehicles on the road, are responsible for moving over 70% of all freight tonnage in the United States. Let us take a deep dive into the most common transport vehicle you see on the I-95 or the I-10, the dry van. On the surface, it is a simple aluminum box on wheels. but the engineering is far more sophisticated than it appears. In 2026, these trailers are built with high-spec aerodynamics. You will notice side skirts hanging beneath the trailer and aerodynamic tails on the rear doors. These are not for aesthetics. They are designed to reduce the low-pressure vacuum that pulls against the back of the truck, which can improve fuel efficiency by over 5%. For a fleet like the one Alex manages, that 5% represents hundreds of thousands of dollars in potential outcomes regarding fuel savings and reduced carbon footprint. Inside these dry vans, the walls are often lined with logistical tracks, allowing for double stacking of pallets. This is crucial because in the world of transport, cubing out is just as bad as grossing out. If a trailer is full of light pillows, it hits its volume limit, or cubes out, long before it hits its weight limit. A professional transport vehicle must be versatile enough to handle both scenarios. Then we have the refrigerated units or reefers. Imagine if Alex has to move a shipment of biological medicine from a lab in Boston to a hospital in Phoenix. This requires more than just a box. It requires a climate-controlled environment. The refrigeration unit on the front of the trailer is a self-contained engine that monitors the internal temperature to within a fraction of a degree. In 2026, these units are increasingly hybrid or fully electric, using large battery banks to keep the cargo cool, even when the main tractor engine is turned off. This is a critical distinction in the definition of a transport vehicle. Many of them are not just movers of mass, but protectors of integrity. Without the specific engineering of the reefer, the global food and pharmaceutical chains would vanish overnight. Consider the flatbed truck, the unsung hero of the American construction industry. Unlike the dry van, the flatbed is designed for cargo that cannot be easily loaded through rear doors or cargo that is overdimensional. When you see a flatbed carrying massive steel I-beams or giant concrete culverts, you are seeing a transport vehicle that relies entirely on structural tension. The securement of the load using winches, straps, and chains is a regulated science. If Alex's drivers do not calculate the aggregate working load limit of their tie-downs, the physics of a sudden stop can turn that cargo into a lethal projectile. This highlights another layer of what a transport vehicle is. It is a platform for specialized securement systems. We also have to look at intermodal transport vehicles. This is where the lines between sea, rail, and road blur. An intermodal chassis is a skeletal frame designed specifically to carry a shipping container. These containers are the bits of the physical world. Just as data is packaged into packets to travel across the internet, goods are packaged into 20 or 40-foot containers to travel across the globe. The transport vehicle in this case is a modular system. The container might start on a massive ship from Busan, be lifted onto a rail car in Long Beach, and finally be locked onto a truck chassis driven by someone in Alex's fleet for the final 50 miles. The engineering of the twist locks that secure the container to the chassis is a marvel of simplicity and strength, ensuring that the container remains part of the vehicle despite vibrations, wind resistance, and centrifugal force during turns. Beyond the highway, we have vocational transport vehicles. These are machines built for one specific job. Think of a cement mixer, or a rear discharge mixer in industry terms. It is not just transporting concrete. It is a mobile manufacturing plant that must keep the material in constant motion to prevent it from hardening. If the drum stops turning, the vehicle effectively becomes a multi-ton block of useless stone. Similarly, specialized heavy-haul vehicles, often featuring 30 or more axles, are used to move massive transformers or aerospace components. These vehicles are so specialized that they often require police escorts and pre-calculated routes to ensure they don't crush underground utilities or get stuck on railroad crossings. Historical trends in the U.S. show that as our cities become more congested, the last-mile transport vehicle is evolving. In 2026, we are seeing the rise of electric walk-in vans and even autonomous delivery pods. These are still transport vehicles, but their design priorities have shifted from high-speed highway stability to low-speed urban agility. They feature high-visibility glass, frequent stop braking systems, and integrated GPS that calculates the most efficient route to save every possible second. So, when we ask what a transport vehicle is, we are asking about the physical manifestation of American demand. Every time you click Buy Now, you are triggering a sequence of events that puts these machines in motion. From the Class 8 tractor trailer to the humble delivery van, these vehicles are the physical infrastructure that makes the digital economy possible. But there is a hidden side to these machines that most people never see. The immense power required to move 80,000 pounds at 70 miles per hour, and the specialized engines that make it happen. In the next part of this masterclass, We are going to crack open the hood and look at the heart of the beast. We will explore why a truck engine is designed to run for 1,000,000 miles while your car might struggle to hit 200,000. We will look at the massive torque required to start a load on a steep grade, and the cooling systems that prevent these engines from melting under the pressure of the American landscape. If you think you understand engines, wait until you see the scale of a commercial power plant. What happens when that engine fails in the middle of the Nebraska plains with 40,000 pounds of perishable goods? How do these machines manage to stop 80,000 pounds of momentum when a car cuts them off in traffic? The answers lie in the specialized mechanical systems that we will break down next. The sheer force of air brakes and the complexity of multi-speed transmissions are what truly separate the transport vehicle from everything else on the road. Do not miss the next chapter of this deep dive into the machines that move America. To truly appreciate the engineering of a transport vehicle, you have to look past the cab and the trailer and focus on the power plant that makes it all possible. Imagine Alex is standing in his maintenance bay in 2026, looking at a disassembled 15-liter heavy-duty diesel engine. This isn't just a larger version of what you find under the hood of a Ford F-150. A standard passenger car engine is built to last perhaps 200,000 miles before requiring a major overhaul. In contrast, the heavy-duty engines used in Class 8 transport vehicles are engineered for a B50 life of 1,000,000 miles. This means that 50% of these engines are expected to cover 1,000,000 miles before needing their first major teardown. This level of durability is achieved through a design philosophy known as wet sleeve construction. In a car, the cylinders are bored directly into the engine block. In a transport vehicle, the cylinders are replaceable liners. If one wears down, you don't throw away the block. You simply swap the sleeve. This is a masterclass in industrial sustainability and cost efficiency. The primary metric of success for these engines isn't horsepower. It is torque. While a high-performance sports car might boast 500 horsepower, it often lacks the low-end grunt needed to move mass. A modern transport vehicle engine in 2026 might produce 600 horsepower, but will generate over 2,000 pound-feet of torque at just 1,100 RPM. Imagine if you were trying to pull a concrete block across a rough floor. Horsepower is how fast you can run once the block is moving. Torque is the raw muscular force required to break the static friction and get it moving in the first place. For Alex, torque is what allows his drivers to start a fully loaded 80,000-pound rig on a 6% grade in the Appalachian Mountains without burning out the clutch or stalling the engine. Now let us look at the cooling system of these machines. A transport vehicle produces a staggering amount of heat when under load. In 2026, we utilize active thermal management systems that are far more advanced than the simple radiators of the past. Imagine a truck climbing the Grapevine in California during a July heat wave. The engine is burning gallons of fuel every few minutes, and the ambient temperature is over 100 degrees. To prevent a catastrophic meltdown, these vehicles use massive radiators, often twice the size of those found in SUVs, paired with multi-stage fan clutches that can draw over 70 horsepower just to move air through the cooling fins. Historical trends show that thermal failure was once the leading cause of roadside breakdowns, but modern sensors now allow the vehicle to derate its own power to protect the engine if temperatures exceed a critical threshold. This is a protective measure where the truck's computer limits speed and RPM to prevent permanent damage, illustrating how the transport vehicle has become a self-aware piece of technology. The transmission is the next critical component in this mechanical deep dive. For decades, the 18-speed manual transmission was the gold standard, requiring a driver to perfectly time their shifts and double clutch to synchronize the gears. However, by 2026, the industry has seen a massive shift toward automated manual transmissions or AMTs. These are not traditional automatics like you find in a car. They are structurally manual gearboxes that use a computer-controlled actuator to shift and manage the clutch. This eliminates human error and ensures the engine always stays in its sweet spot for fuel efficiency. The potential outcomes of this shift include reduced driver fatigue and significantly improved fuel economy across the fleet. Alex has seen his fleet's average fuel mileage rise from 6 miles per gallon to nearly 9 miles per gallon, simply by transitioning to these advanced AMTs and optimizing the gear ratios for the specific terrain his drivers face. But moving the vehicle is only half the battle. Stopping it is where the real physics begins. A transport vehicle does not use the hydraulic brakes you have in your car. If a hydraulic line leaks in your car, you lose braking pressure. In a transport vehicle, we use air brakes. This is a fail-safe system. Compressed air is used to hold the spring brakes open. If the system loses pressure, meaning there is a leak or a catastrophic failure, the massive steel springs are released, and the brakes are automatically applied with full force. This is why you sometimes see skid marks on the highway that lead to a stopped truck. If the air pressure drops below 60 psi, the vehicle essentially decides to stop itself for safety. The actual stopping power comes from the S-cam drum brake, or the increasingly popular air disc brake. In a drum system, the air pressure forces brake shoes outward against a rotating drum. In a disc system, pads are squeezed against a rotor. Imagine the friction generated when you try to stop 80,000 pounds of momentum traveling at 70 miles per hour. The brake components can reach temperatures of over 600 degrees in a single heavy braking event. To manage this, transport vehicles use engine retarders, commonly known as jake brakes. This system essentially turns the engine into an air compressor, using the engine's internal compression to slow the vehicle down without using the friction brakes at all. When you hear that deep, rhythmic brop-brop sound from a truck on a mountain pass, you are hearing the engine retarder at work, saving the life of the brake pads and preventing brake fade, a dangerous condition where the brakes get so hot they lose their ability to create friction. In 2026, the definition of the transport vehicle's drivetrain is expanding to include zero-emission options. In urban environments, Alex is increasingly deploying Class 6 electric transport vehicles. These machines replace the diesel engine with high-torque electric motors and massive lithium iron phosphate battery packs. While they lack the million-mile range of a diesel engine for cross-country hauls, they are perfect for the stop-and-go torture of city delivery. The regenerative braking in these electric transport vehicles allows them to capture the energy of slowing down and put it back into the battery, a feat of efficiency that was a pipe dream only a decade ago. The complexity of these systems means that a transport vehicle is never truly off. Even when parked, the telematics systems are communicating with Alex's office, reporting on engine health, brake wear, and fuel levels. This brings us to a critical realization. A transport vehicle is not just a tool, it is a high-performance athlete. It requires constant monitoring, specialized fluids, and a deep understanding of the laws of physics to operate safely on American roads. We have seen how these machines are built to survive and how they use air and fire to move the nation's goods. But what happens when the road itself becomes the enemy? How do these vehicles navigate the legal and physical minefields of the American landscape? Beyond the engine and the brakes, there is a complex world of aerodynamics, weight sensors, and specialized tires that allow these giants to glide through the air and grip the road in any weather. In the next part of this masterclass, we are going to look at the skin and the tires. We will explore how a single tire can cost $500 and why it is designed with specific tread patterns for different axles. We will also dive into the ghost in the machine, the advanced driver assistance systems that use radar and cameras to see accidents before they happen. What is the true cost of operating these machines per mile? And how do the tires on a transport vehicle manage to carry 10 times the weight of a car tire without exploding? The answers will change the way you see every vehicle on the road. Stay tuned because we are about to peel back the next layer of the American transport machine. The engineering of a transport vehicle does not stop at the engine or the frame. It extends to the very point where the machine meets the earth. To understand the scale of what we are discussing, we have to look at the rubber. In 2026, a single heavy-duty tire for a Class 8 vehicle can cost between $500 and $800 depending on its application. When you realize a standard 18-wheeler is carrying $10,000 worth of rubber at any given time, the economic stakes become clear. Alex, our fleet manager in Indianapolis, spends a significant portion of his annual budget just on tire management, and for good reason. These tires are not universal. They are specialized tools designed for specific positions on the vehicle, known as steer, drive, and trailer positions. Steer tires are the most critical. Located on the front axle, they are designed with longitudinal ribs to provide directional stability and shed water efficiently to prevent hydroplaning. Because they are responsible for steering 80,000 pounds, they are engineered with reinforced sidewalls to handle the immense lateral forces of turning. If a steer tire fails at highway speeds, the potential outcomes are catastrophic. This is why historical trends in the industry show a zero-tolerance policy for retreading steer tires. They must always be virgin rubber. Drive tires, conversely, are the muscles. They feature aggressive lug patterns to bite into the pavement, providing the traction necessary to move the mass. In 2026, these treads are designed using computational fluid dynamics to minimize rolling resistance while maximizing grip. Finally, trailer tires are built for one thing: efficiency. They have shallower treads and are designed to follow the tractor with as little friction as possible. The physics of a transport tire are mind-bending. While your car tire might be inflated to 35 pounds per square inch, a transport vehicle tire is often pressurized to 100 or 110 psi. Imagine the internal tension within that casing. Under a full load, the internal temperature of the tire can exceed 150 degrees Fahrenheit. If the pressure drops even 10%, the sidewall flexes too much, generating heat that can lead to a blowout, or what truck drivers call a road gator. Those massive strips of black rubber you see littering the shoulders of American interstates. In 2026, Alex's fleet uses automatic tire inflation systems that sense a leak and pump air from the vehicle's air tanks directly into the tire, while the truck is moving at 70 miles per hour. This is the level of sophistication required to keep the American supply chain from quite literally deflating. Now, let us look at the skin of the vehicle, the aerodynamics. At highway speeds, a transport vehicle is essentially a massive, unaerodynamic brick fighting a war against the atmosphere. Over half of the fuel consumed by a truck at 65 miles per hour is used simply to push air out of the way. This is why the appearance of transport vehicles has changed so drastically in the last decade. In 2026, Alex's trucks are equipped with a full suite of aerodynamic fairings. You have the roof fairing that directs air over the trailer, the chassis fairings that cover the fuel tanks to prevent turbulence around the wheels, and the trailer side skirts that keep air from getting trapped under the trailer and creating a low-pressure drag. But the most fascinating advancement is the gap fairing and the boat tail. The 3-foot gap between the tractor and the trailer is a vortex of wasted energy. Modern transport vehicles use extenders to bridge this gap, ensuring a laminar flow of air. At the very back of the trailer, you will see 4-foot-long folding panels known as boat tails. These panels taper the airflow as it leaves the vehicle, reducing the wake of dirty air that pulls the truck backward. For a fleet operating millions of miles, these pieces of plastic and aluminum are not accessories. They are high-return investments. Data shows that a fully aero-optimized rig can achieve a 10 to 15% improvement in fuel economy over a naked truck. In an industry where profit margins are often thin, that efficiency is the difference between a thriving business and a failing one. Beyond the physical skin lies the ghost in the machine, the Advanced Driver Assistance Systems, or ADAS. In 2026, the definition of a transport vehicle includes its digital perimeter. Imagine a driver named Sarah navigating Alex's truck through a blinding rainstorm on I-80. She cannot see the car that has spun out 300 feet ahead, but the truck can. Using a combination of 77 GHz radar and high-definition LiDAR mounted in the bumper, the vehicle's collision mitigation system is constantly scanning the horizon. If it detects a closing speed that suggests an imminent impact, it doesn't just warn Sarah. It takes control. The system can apply full braking force faster than a human can move their foot from the accelerator to the brake pedal. This technology has transformed the transport vehicle into a proactive safety device. Historical trends indicate that rear-end collisions, once the most common and deadly type of truck accident, have plummeted as these systems have become standard. We also have lane keep assist, which uses cameras to track road markings. If Sarah's truck begins to drift due to a crosswind or a moment of fatigue, the steering column applies a subtle torque to nudge the 80,000-pound machine back into the center of the lane. This isn't full autonomy yet, but it is a sophisticated partnership between human and machine. Furthermore, the 2026 transport vehicle is a rolling data center. Every sensor, from the tire pressure monitor to the radar unit, is fed into a telematics gateway. Alex can sit in his office in Indianapolis and see the exact health of every vehicle in his fleet in real time. If a sensor on Sarah's engine detects a slight increase in soot levels in the diesel particulate filter, the system can automatically schedule a maintenance appointment at a shop located on her route before a breakdown even occurs. This is known as predictive maintenance, and it has revolutionized the uptime of American transport. The cost of operating these machines is staggering. When you factor in the $5 a gallon diesel, the $1,000 tires, the insurance premiums, and the specialized maintenance, it costs Alex's company roughly $2.50 for every single mile a truck moves. If a truck drives 100,000 miles a year, that is $250,000 in operating costs per vehicle. This is why every detail, from the tread on the tire to the curve of the side skirt, is engineered to a microscopic degree. The transport vehicle is a machine that exists in a state of constant optimization. As we have seen, the transport vehicle is a masterpiece of physical and digital engineering. It is a beast of burden that uses air to stop, fire to move, and lasers to see. But these machines do not operate in a vacuum. They are part of a massive, invisible network that dictates every move they make. Who decides which route a truck takes? How do we coordinate millions of these giants so they don't all end up in the same place at the same time? In the next part of this masterclass, we are going to look at the brains of the operation. We will dive into the world of logistics software, load boards, and the federal regulations that govern the life of a driver. We will explore the hours of service laws that dictate when a driver must sleep, and how the government tracks their every move via satellite. We will also look at the complex world of freight factoring, and how the money actually flows in this multi-billion-dollar industry. You might know how the truck moves, but do you know how the industry thinks? The answer is more complex than you can imagine. Stay with us as we move from the machine to the mind of American transport. The transition from the mechanical parts of a transport vehicle to its operational mind begins with a piece of technology that has fundamentally changed the life of every driver in the United States: the electronic logging device, or ELD. In 2026, the ELD is not just a digital diary. It is a hardwired component of the vehicle's engine control module. It monitors exactly when the wheels are in motion, tracking every second of a driver's day with zero room for the creative bookkeeping that once defined the industry. Imagine Sarah, a professional driver in 2026, pulling out of a terminal in New Jersey. The moment her truck exceeds 5 miles per hour, the ELD automatically switches her status to driving. From that second, she is racing against a set of federal regulations known as the Hours of Service, or HOS. To understand the HOS, you have to look at the 3 primary clocks Sarah must manage. First is the 11-hour driving limit. After 10 consecutive hours off duty, Sarah is permitted to drive for a maximum of 11 hours. Second is the 14-hour workday limit. Once she starts any kind of work, whether it is pre-trip inspections, loading, or driving, a 14-hour countdown begins that cannot be paused. Even if she sits in traffic for 3 hours, the clock keeps ticking. Third is the 60 or 70-hour limit over a 7 or 8 day period. This is the macro-level view of her exhaustion. If Sarah hits her 70 hours in 6 days, her transport vehicle becomes a multi-ton paperweight until she completes a 34-hour restart, which is a mandated period of rest to reset her weekly clock. The pressure of these clocks creates a high-stakes environment. Imagine if Sarah is 20 miles away from her delivery point in Chicago, but she has only 15 minutes left on her 14-hour clock. Under federal law, she must stop. She cannot simply push through the final few miles. If she does, and an inspection occurs or an accident happens, the potential outcomes for both her and the fleet manager, Alex, are severe. The FMCSA, or Federal Motor Carrier Safety Administration, uses a system called CSA, Compliance, Safety, Accountability, to track these violations. Every time a truck is inspected, the results are fed into a national database. High scores in categories like unsafe driving or HOS compliance can lead to increased insurance premiums, frequent roadside pullovers, and even the loss of the company's operating authority. In 2026, a transport vehicle's most important feature isn't its engine displacement, it is its safety rating. Now, how does the cargo actually find the truck? In 2026, we operate in a digital marketplace dominated by load boards and AI-driven freight matching. Gone are the days of phone calls and fax machines. Today, Alex uses platforms like DAT1 or Truckstop.com, along with specialized 2026 AI aggregators that predict freight lane fluctuations. When a manufacturer in Ohio has 50,000 pounds of steel coils that need to go to a factory in Texas, they post it to the spot market. This is a massive real-time auction where thousands of carriers bid on the shipment. The math of booking a load is a masterclass in microeconomics. Alex has to calculate the all-in rate. This includes the base rate per mile, which in 2026 might fluctuate between $2 and $4, plus the fuel surcharge. The fuel surcharge is a critical mechanism that protects carriers from the volatility of diesel or electricity prices. If fuel prices spike, the surcharge increases, ensuring the transport vehicle can keep moving without bankrupting the owner. Alex also has to consider deadhead miles, the distance Sarah must drive empty to pick up the load. If a load pays $3 a mile but requires 200 miles of deadhead, the actual profitability drops significantly. Historical trends show that the most successful fleets are those that minimize deadhead through sophisticated route optimization software that weaves Sarah through a daisy chain of loads across the country. Once the load is delivered, a new challenge arises: getting paid. In the American transport industry, Standard payment terms from shippers are often 30, 60, or even 90 days. For a small fleet like Alex's, waiting 90 days to get paid for a $10,000 haul is impossible when the fuel and driver wages must be paid immediately. This is where freight factoring comes in. Alex sells his invoices to a factoring company. For a small fee, usually between 1 and 3%, the factoring company pays Alex within 24 hours and then takes on the responsibility of collecting the full amount from the shipper. While it is a cost of doing business, it is the grease that keeps the wheels of the American economy turning. It provides the liquidity necessary to maintain the transport vehicles and keep the supply chain fluid. The mind of the transport vehicle also includes its communication with the infrastructure itself. In 2026, Vehicle-to-Infrastructure, or V2I technology is being rolled out across major U.S. corridors. Sarah's truck can communicate with way stations while she is still miles away. Systems like PrePass or DriveWise allow the way station's computers to check the truck's weight, its safety credentials, and its carrier CSA scores in a fraction of a second. If everything is green, Sarah receives a signal in her cab allowing her to bypass the scale, saving fuel and time. This is a massive efficiency gain for the national transport network. But what about the cargo itself? In this part of the masterclass, we have discussed the driver's mind and the manager's math, but the cargo has its own set of requirements. Some loads are so heavy they require special permits. Some are so dangerous they require placards and specialized routing away from tunnels and major cities. These are the hazardous materials, or hazmat regulations. A transport vehicle carrying thousands of gallons of gasoline or pressurized chemicals is subject to a completely different level of scrutiny. The driver must have specialized endorsements on their commercial driver's license, or CDL, and the vehicle must be inspected with surgical precision every single day. As we look at the complexity of the logistics, the regulations, and the financial structures, we see that the transport vehicle is the physical execution of a massive data-driven plan. It is a machine that operates at the intersection of physics, law, and economics. But there is one final piece of the puzzle that often goes unnoticed: the environment inside the cab. For Sarah, this truck is not just a machine or a data node. It is her home. In 2026, the sleeper berth of a long-haul transport vehicle is a miracle of space-efficient engineering. What does it actually feel like to live and work inside a machine for weeks at a time? How do these vehicles provide the electricity, climate control, and connectivity required for a human to survive in the middle of a truck stop in Wyoming? In the next part of this masterclass, we are going to step inside the cab and explore the living quarters of the American road. We will look at auxiliary power units that keep the lights on without idling the main engine, the ergonomics of a seat that costs more than a high-end sofa, and the mental toll of the lone wolf lifestyle. We will also dive into the future of platooning, where multiple trucks electronically link up to save fuel, and how that changes the very nature of driving. The machine is impressive, but the life of the person behind the wheel is the true heart of the story. Do you have what it takes to live in 8 square feet while moving 80,000 pounds? You are about to find out. To step into the cab of a modern Class 8 transport vehicle in 2026 is to enter a masterpiece of high-density living and industrial ergonomics. Sarah, our veteran driver, begins her day by transitioning from her sleeper berth to the driver's seat. This transition is only a distance of about 3 feet, but it represents the move from her private residence to her high-stakes office. The seat she sits in is not merely a chair. It is a $5,000 piece of specialized equipment known as an active suspension seat. Historical trends in the trucking industry once showed that chronic back pain and spinal compression were the primary reasons drivers left the profession. To combat this, 2026 transport vehicles use seats equipped with internal air compressors and sensors that adjust the seat's vertical movement up to 200 times per second. If Sarah hits a massive pothole on a bridge in Pennsylvania, the seat's computer reacts in milliseconds, neutralizing the shock before it can travel up her spine. This is the level of engineering required when your office chair is hurtling down a highway for 11 hours a day. Looking forward from that seat, the dashboard is a digital cockpit. In 2026, physical gauges have largely been replaced by customizable high-definition displays. These screens provide Sarah with more than just speed and fuel levels. They show her the real-time weight on every single axle, the current aerodynamic drag coefficient, and the status of her collision mitigation sensors. This is critical because a transport vehicle's performance changes based on the environment. If she is driving through a crosswind in Wyoming, The truck stability control system can actually apply microbraking to individual wheels to keep the trailer from swaying. This digital layer is what makes the modern transport vehicle a smart machine rather than just a mechanical one. Now let us turn around and look at the sleeper berth. In the United States, the Department of Transportation has strict requirements for what constitutes a legal sleeper berth. It must be at least 75 inches long and 24 inches wide, but in 2026, most long-haul rigs feature 72 to 80-inch raised roof sleepers. Imagine if you had to fit a bed, a desk, a refrigerator, a microwave, and a wardrobe into a space the size of a walk-in closet. This is the reality of the American road. To keep Sarah comfortable during her mandatory 10-hour break, the vehicle uses an auxiliary power unit, or APU. In the past, drivers had to idle the massive 15-liter main engine all night just to keep the air conditioning running, which consumed a gallon of fuel every hour and caused immense wear on the engine. In 2026, Sarah's truck is equipped with an electric APU powered by a dedicated lithium-ion battery bank. It provides silent, zero-emission climate control and electricity for her devices. This allows her to run an air fryer or a gaming laptop without ever turning the ignition key. The lifestyle of the lone wolf driver like Sarah is one of extreme discipline. Every meal is a logistical calculation. Many drivers in 2026 have moved away from expensive and often unhealthy truck stop food, instead utilizing their in-cab kitchens to prepare meals. This is not just about health, it is about the math of the road. If Sarah spends 30 minutes looking for parking at a crowded truck stop just to get a burger, she is burning precious time on her 14-hour clock. By remaining in her transport vehicle, she maintains control over her schedule and her health. Connectivity is the final piece of this lifestyle puzzle. With 2026-era satellite internet terminals mounted on the roof fairings, Sarah has high-speed connectivity even in the dead zones of the Mojave Desert. This allows for real-time video calls with family and seamless updates to her electronic logging device, reducing the psychological toll of the isolation that defines long-haul transport. However, not all transport vehicles are operated by a single person. Let us look at a case study of a team driving operation, often referred to as the rolling apartment. Imagine a husband and wife team, the Millers. In their Class 8 rig, the truck almost never stops. While one spouse drives their 11-hour shift, the other is sleeping in the back. This requires a specialized bunk restraint system, a heavy-duty netting that ensures the sleeping partner is not thrown from the bed during a sudden braking event. Team driving is the pinnacle of transport efficiency. A solo driver like Sarah might take 5 days to move a load from New Jersey to California due to mandatory rest periods. The Millers can do it in less than 48 hours. For high-value, time-sensitive cargo like fresh seafood or the latest electronics, the transport vehicle becomes a perpetual motion machine, stopping only for fuel and driver swaps. As we look toward the future of 2026 and beyond, the way these vehicles interact on the road is changing through a technology called platooning. Imagine 3 of Alex's trucks traveling down I-80 in a perfectly synchronized line, separated by only 20 feet. This is made possible by vehicle-to-vehicle, or V2V, communication. The lead truck acts as the brain, and the following trucks are electronically tethered to it. When the lead driver brakes, the following trucks brake instantaneously, far faster than a human could react. The potential outcomes of platooning are massive. The following trucks sit in the aerodynamic slipstream of the leader, reducing fuel consumption by up to 10% for the second truck and 15% for the third. This turns a group of individual transport vehicles into a single cohesive logistical train on rubber tires. But the complexity of living and working in these machines brings us to a darker reality. What happens when things go wrong? When you are moving 80,000 pounds, the margin for error is non-existent. The transport vehicle is subject to a level of scrutiny that no passenger car will ever face. Every year, thousands of trucks are pulled into roadside inspection bays where highly trained DOT officers crawl under the chassis with creepers and flashlights, looking for a single freight airline or a brake pad that is 1/16 of an inch too thin. A single failure in any of these systems can result in the vehicle being placed out of service on the spot, meaning it cannot move an inch until it is repaired. In the next part of this masterclass, we are going to dive into the high-stakes world of the inspection and the law. We will look at exactly what a DOT officer is looking for during a Level 1 North American Standard inspection. We will explore the safety measurement system and how a single broken taillight can affect a company's ability to win contracts with major retailers. We will also examine the legal aftermath of a commercial vehicle accident the black box data that reveals exactly what the driver was doing in the seconds before impact. If you thought the mechanics were intense, wait until you see the legal and regulatory web that surrounds every wheel of an American transport vehicle. The road is a courtroom, and the stakes are higher than you can imagine. Stay tuned for the deep dive into the rules of the road. Imagine Sarah is approaching a port of entry on the outskirts of Columbus, Ohio, in the spring of 2026. She is moving 80,000 pounds of high-grade industrial plastics. As her Class 8 transport vehicle rolls over the weigh and motion sensors embedded in the highway, a high-speed camera captures her DOT number and her license plate. In the scale house, a Department of Transportation officer sees a green light on his monitor, but today is the day for a random inspection. He toggles the signal, and Sarah's in-cab transponder chirps with a red light, signaling her to pull into the inspection bay. This is the moment where the mechanical reality of the transport vehicle meets the unyielding force of American law. To understand the legal definition of a transport vehicle, you have to understand the North American Standard Level 1 inspection. This is a 37-step procedure that is arguably the most rigorous roadside safety check in the world. Officer Miller, a 20-year veteran of the State Highway Patrol, approaches Sarah's truck with a clipboard and a heavy-duty creeper. This isn't a quick glance. It is a surgical examination. He begins with the driver's credentials. He checks her commercial driver's license, her medical examiner's certificate, and her record of duty status on the electronic logging device. In 2026, any discrepancy in these documents can result in an immediate out-of-service order. But the paperwork is just the prologue. Officer Miller moves to the front of the vehicle. He checks the steering system for any play in the steering column or worn-out tie rod ends. He examines the suspension, looking for cracked leaf springs or leaking shock absorbers. Then he slides under the chassis on his creeper to inspect the heart of the vehicle's safety, the air brake system. This is where most inspections are won or lost. He uses a specialized tool to measure the brake stroke. If the pushrod on a single brake chamber moves more than 2 inches when the brakes are applied, the truck is legally unsafe to operate. This is because at highway speeds, even a minor imbalance in braking force can cause a jackknife or a runaway truck scenario. Historical trends show that brake-related issues account for nearly 30% of all out-of-service violations in the United States. He continues down the line, checking the frames, the fuel tanks, and the cargo securement. Sarah has to show that her steel straps are not frayed and that her winches are locked tight. He inspects the tires for a minimum tread depth of 4/32 of an inch on the steer tires and 2/32 on the drive tires. In 2026, with the prevalence of high-torque electric and hybrid drivetrains, tire wear patterns have changed, and Officer Miller is looking for signs of irregular cupping that could indicate a suspension failure. If he finds a single major violation, Sarah's journey ends right there in the parking lot. She will be placed out of service, and her carrier, Alex, will have to pay for a mobile repair unit to come to the scale house at an exorbitant cost. But the consequences go far beyond a repair bill. Every inspection result is uploaded to the Safety Measurement System, or SMS, which is part of the FMCSA's Compliance, Safety, Accountability Program. Think of the SMS as a credit score for transport companies. It categorizes violations into 7 behavior analysis and safety improvement categories, known as basics. These include unsafe driving, fatigue driving, driver fitness, controlled substances, vehicle maintenance, cargo securement, and the crash indicator. Each violation is weighted based on its severity and how recently it occurred. Imagine if Alex's fleet starts accumulating points in the vehicle maintenance category because of recurring brake issues. This creates a feedback loop. A high SMS score acts as a red flag to every other DOT officer in the country, making Alex's trucks much more likely to be pulled in for future inspections. Furthermore, major shippers like big box retailers and automotive manufacturers monitor these scores religiously. They will not hire a carrier with a poor safety rating because of the potential outcomes regarding liability. If a carrier with a high SMS score is involved in an accident, the legal repercussions are devastating. This brings us to the dark side of the transport industry, the nuclear verdict. In the United States legal system of 2026, lawsuits against trucking companies often result in judgments exceeding $10 million. To protect themselves, transport vehicles are now equipped with what is colloquially known as the black box, or the event data recorder. In the seconds before a collision, this device records everything: GPS coordinates, speed, throttle position, brake pressure, and steering angle. When combined with the 2026 standard AI dash cams that monitor both the road and the driver, the transport vehicle becomes a witness in its own trial. Case studies from the past 5 years show that this data is the primary tool for exonerating drivers. Imagine a passenger car suddenly swerves in front of Sarah's 80,000-pound rig and slams on the brakes. Without data, it might look like Sarah was at fault for a rear-end collision. But the black box proves that Sarah reacted in 0.5 seconds, that her brakes were perfectly maintained, and that the car's deceleration was physically impossible for a heavy vehicle to match. This data doesn't just save Sarah's career. It saves Alex's entire company from a bankruptcy-inducing settlement. However, the law doesn't just care about safety. It cares about the road itself. This is why transport vehicles are subject to the federal bridge formula. This law prevents heavy vehicles from concentrating too much weight on a small section of a bridge. Sarah has to ensure her axles are slid to the correct position to distribute the weight across the maximum distance. If she is overweight on her tandem axles, even if her total weight is under 80,000 pounds, she is in violation. This is the constant mental load of the driver. You are a mechanic, a lawyer, a mathematician, and a pilot all at once. Operating a transport vehicle in 2026 means living in a glass house. Every move is tracked, every bolt is regulated, and every mistake is recorded. But there is a reason for this intensity. When an 80,000-pound machine travels at 70 miles per hour, it possesses as much kinetic energy as a small explosion. The regulations are the only thing that keeps that energy channeled into productive commerce rather than destructive chaos. As we have seen, the transport vehicle is a prisoner of the law, held to a standard of perfection that no other vehicle on the road must meet. But as the world changes, so does the nature of what we are transporting and how we power these giants. The legal web is tight, but the environmental web is even tighter. In the next part of this masterclass, we are going to look at the green revolution. We will explore how the transition to hydrogen and electric power is redefining the mechanics of the transport vehicle. What happens when you replace a diesel tank with a high-pressure hydrogen cell? How do you keep an 80,000-pound electric truck from crushing the very roads it is trying to save? And most importantly, who is going to pay for the trillion-dollar infrastructure shift required to keep America moving? The future of the transport vehicle is electric, but the path to get there is full of friction. You won't want to miss the breakdown of the fuels of tomorrow. The friction of the transition to a green transport economy begins with a single unyielding law of physics: energy density. To understand why Alex is hesitant to replace his entire fleet of diesel trucks with electric ones in 2026, we have to look at the math of the battery. Diesel fuel is a miracle of energy storage, containing about 12 kilowatt-hours of energy per kilogram. In contrast, the high-end lithium-ion batteries found in 2026 transport vehicles struggle to hit even 0.3 kilowatt-hours per kilogram. This means that to get the same range as a few hundred gallons of diesel, you need a battery pack that weighs tens of thousands of pounds. Imagine Sarah is driving a fully electric Class 8 tractor. Her battery pack alone might weigh 15,000 pounds. In the world of transport, weight is the enemy of profit. Every pound of battery is a pound of cargo she cannot legally carry. To mitigate this, the United States government has implemented a 2,000-pound weight allowance for zero-emission vehicles, allowing Sarah to gross 82,000 pounds. However, even with this exemption, the potential outcomes for payload capacity remain a primary concern for fleet managers across the country. The second barrier is the sheer scale of the power required. When Sarah pulls her electric transport vehicle into a charging station in 2026, she isn't using a standard level 2 charger like you would for a car. She is plugging into a megawatt charging system, or MCS. These chargers are designed to deliver over 1 megawatt of power, enough to power a small neighborhood. To charge a 600 kilowatt-hour battery in 30 minutes requires a massive amount of infrastructure. Historical trends show that the American electrical grid was never designed for this kind of concentrated, high-voltage demand. For Alex to install 10 of these chargers at his Indianapolis terminal, he would need a dedicated substation from the local utility company, a project that can cost millions of dollars and take years to permit. This is the hidden cost of the transport vehicle's evolution. The machine is only as good as the wire it is plugged into. This energy density problem is why the industry is looking intensely at hydrogen fuel cell vehicles, or FCEVs. Imagine a transport vehicle that carries high-pressure tanks of hydrogen gas instead of massive batteries. Through a chemical process in the fuel cell, the hydrogen is converted into electricity to power the motors, with the only emission being pure water vapor. For Sarah, the advantage is speed. Refueling a hydrogen truck takes about 15 to 20 minutes, roughly the same as diesel, and the system is significantly lighter than a battery pack. However, the 2026 landscape for hydrogen is still a work of progress. The United States is currently developing hydrogen hubs across the Midwest and California, but until a driver can find a hydrogen station as easily as a Love's or a Pilot Travel Center, the FCEV remains a regional tool rather than a cross-country king. Case studies from 2025 and 2026 reveal a split in the transport vehicle market. For regional haulers, trucks that travel less than 200 miles and return to the same base every night, electric power is winning. These vehicles can charge overnight when electricity rates are lower, and their predictable routes eliminate range anxiety. But for the long-haul sleeper cab market, the diesel engine remains the incumbent champion. Alex has realized that a one-size-fits-all approach no longer works. His fleet in 2026 is a mosaic of technologies. He has electric vans for last-mile delivery, hydrogen-ready tractors for mid-range hauls, and high-efficiency clean diesel rigs for the 3,000-mile treks from Seattle to Miami. The evolution of the transport vehicle also includes the fuel itself. We are seeing a massive rise in renewable diesel or RD. Unlike traditional biodiesel, which can be hard on engines in gel in cold weather, renewable diesel is a drop-in fuel chemically identical to petroleum diesel, but made from fats, oils, and greases. For Sarah, it means she can drive a traditional internal combustion engine with a carbon footprint that is up to 80% lower. This is a critical bridge technology for the American transport industry. It allows companies to meet environmental goals without scrapping their multi-million-dollar investments in existing vehicles. But as the power source changes, so does the maintenance. Imagine a technician in Alex's shop in 2026. He is no longer just a mechanic with a wrench. He is a high-voltage specialist in a protective suit. Working on an electric transport vehicle involves managing 800-volt systems that can be lethal if handled incorrectly. The complexity of these machines has led to a shift in the labor market. The 2026 transport vehicle requires a workforce that understands power electronics, thermal management systems for batteries, and sophisticated software diagnostics. This transition has a direct impact on the cost per mile. While electric trucks have fewer moving parts, no oil changes, no transmission fluid, no exhaust after treatment, the cost of replacing a degraded battery pack 5 years down the line is a financial cliff that Alex must carefully plan for. Furthermore, we must address the source of energy debate. If Sarah's electric truck is being charged by a coal-fired power plant in the Ohio River Valley, is it truly a green transport vehicle? In 2026, the concept of well-to-wheel emissions has become the standard for measurement. Fleet managers are increasingly looking for green hydrogen, produced by electrolysis using wind or solar power, rather than gray hydrogen made from natural gas. The transport vehicle is no longer an isolated machine. It is the final link in an energy chain that starts at a wind farm or a nuclear reactor. The physical design of the vehicle is also changing to accommodate these new fuels. Without a massive diesel engine and its associated cooling needs, the front of the truck can be made more aerodynamic. In 2026, we are seeing the return of the cab-over design in electric trucks, but with a futuristic, curved profile that looks like a high-speed train. By moving the driver further forward and smoothing out the nose, these vehicles can achieve even higher efficiency, clawing back some of the range lost to the weight of the batteries. The green revolution in transport is not just about saving the planet. It is about survival in a new regulatory environment. In 2026, states like California have mandated that a certain percentage of all new truck sales must be zero emission. This is a massive shift for the American market. It is forcing manufacturers like Freightliner, Kenworth, and Peterbilt to reinvent themselves. We are witnessing the most significant period of innovation in the history of the transport vehicle since the invention of the diesel engine itself. But as we look at these sleek, silent electric giants, we have to remember that not all transport is about efficiency and environment. Some jobs are so massive, so dangerous, or so specialized that they require a completely different breed of machine. What happens when you need to move a 300-ton transformer across a mountain range? What happens when the cargo is so explosive that the vehicle requires its own security detail and a specialized route through the desert? In the next part of this masterclass, we are going to look at extreme transport. We will dive into the world of oversized loads, multi-trailer road trains in the American West, and the specialized heavy haulers that move the literal building blocks of our civilization. These are the monsters of the road, and their engineering is on a scale that defies belief. If you thought a semi-truck was big, you haven't seen anything yet. Stay tuned as we go big, really big. To enter the world of extreme transport is to witness the absolute limits of terrestrial engineering. Imagine Alex has been tasked with moving a 400-ton power transformer from a port in Houston to a substation in the heart of the Texas Hill Country in 2026. This is not a job for a standard 18-wheeler. This is a superload. In the United States, a superload is any transport vehicle and cargo combination that exceeds the standard permit limits for weight, height, or width, often reaching weights of over 500,000 pounds and lengths of over 200 feet. To move this mass without collapsing a bridge or tearing up the interstate, we use a specialized machine known as a modular hydraulic trailer. These trailers are a masterclass in weight distribution. Imagine a platform with 48 or even 64 independent wheels, each mounted on a hydraulic suspension system. These wheels are not just following the truck, they are active participants in the journey. In 2026, these modular units are often equipped with electronic multi-mode steering. This allows the rear of a 200-foot-long transport vehicle to crab steer sideways or pivot around a central axis, navigating 90-degree turns in small-town intersections that would be physically impossible for a standard trailer. The hydraulic suspension allows the operators to raise or lower the entire load by several feet, enabling the vehicle to clear low-hanging power lines or pass over high-centered railroad crossings. This is the ultimate expression of the transport vehicle, a machine that can be custom configured for a single, high-stakes mission. The physics of a superload requires more than just one engine. In many case studies from 2026, you will see a push-pull configuration. At the front, a high-torque heavy-haul tractor provides the pulling force. At the rear, a second tractor, the pusher, is linked to the trailer, providing additional power for steep grades and extra braking force for descents. The drivers of these two vehicles must operate in perfect synchronization, often communicating via headsets to manage throttle and gear changes simultaneously. If the lead driver shifts gears while the pusher is still at full throttle, the resulting jolt could snap a hitch or destabilize the entire 400-ton assembly. This is high-stakes coordination where the potential outcomes of a single mistake are measured in millions of dollars of infrastructure damage. But extreme transport isn't just about weight, it is also about length. In the vast stretches of the American West, particularly in states like Nevada, Utah, and Montana, we see the operation of LVCs or longer combination vehicles. These are the road trains of America. While the standard U.S. truck pulls a single 53-foot trailer, an LVC might consist of 3 28-foot trailers, known as a triple, or 2 full-size 48-foot trailers, known as a turnpike double. The engineering that allows these road trains to operate safely at highway speeds is centered on the converter dolly. This is a small unpowered trailer with its own fifth wheel that connects the rear of one trailer to the front of the next. In 2026, these dollies are equipped with their own ABS and stability control sensors, ensuring that the whip effect, where a small movement at the front of the truck becomes a violent sway at the back of the third trailer, is electronically neutralized before it can cause a rollover. The logistics of moving these giants is a masterclass in bureaucratic and physical preparation. For Alex to move that transformer, he must first commission a route survey. This is a 300-page document that analyzes every bridge, every overpass, and every utility wire along the 500-mile route. Historical trends show that even a 1-inch miscalculation in the height of an overpass can lead to a catastrophic collision. To prevent this, the transport vehicle is preceded by a pilot car equipped with a high pole, a fiberglass rod set exactly 6 inches higher than the load. If the pole hits a wire or a bridge, the pilot car alerts the truck driver to stop immediately. Behind the truck, a chase car manages traffic, ensuring that passenger vehicles do not get caught in the blind zones of the massive rig. In 2026, these pilot cars are increasingly integrated with the truck's dashboard, providing a live LiDAR map of the road ahead to detect obstacles in real time. Then there is the category of vocational monsters that never touch a public highway. Consider the mining haul truck, such as the Caterpillar 797 or the Komatsu 980E. These are transport vehicles on a scale that defies human intuition. A single tire on one of these machines stands 13 feet tall and costs over $40,000. These trucks are designed to carry 400 tons of, or in a single trip, 24 hours a day, in the most brutal environments on Earth. In 2026, many of these mining giants have transitioned to autonomous operation. They navigate the labyrinthine paths of open-pit mines in Arizona and Minnesota using GPS and radar, moving millions of tons of material with a precision that human drivers struggle to match. These are not just trucks, they are mobile pieces of industrial infrastructure. The aerospace industry provides another fascinating example of extreme transport. Imagine the journey of a rocket booster from a factory in New Orleans to the launch pad at Kennedy Space Center. Because of their immense size and fragility, these components are often moved on specialized barges or inside Super Guppy aircraft. However, for the final land-based leg, they are placed on self-propelled modular transporters, or SPMTs. These vehicles do not have a traditional tractor. They are powered by internal hydraulic power packs and controlled by an operator with a remote control pendant walking alongside the vehicle. The SPMT can move in any direction, sideways, diagonally, or even spinning in a circle. This level of maneuverability is the only way to move a multi-billion-dollar piece of space hardware through the tight confines of a launch facility. As we look at these extreme machines, we see that the definition of a transport vehicle has expanded to include anything that can reliably displace mass across distance, regardless of the scale. From the multi-axle superload trailers to the autonomous mining trucks and the modular transporters of the space age, these vehicles represent the pinnacle of human mechanical achievement. They are the tools we use to build our cities, power our homes, and reach for the stars. They are the heavy metal that makes our modern existence possible. But after exploring the engines, the tires, the laws, the green revolution, and the extreme monsters of the road, we have to ask, where is it all going? We have seen the 2026 reality of human-driven trucks and hybrid fleets, but we are on the precipice of a shift that will change the American landscape forever. In the final part of this masterclass, we are going to synthesize everything we have learned and look at the final destination of the transport vehicle. We will explore the reality of fully autonomous hub-to-hub trucking, the integration of drone delivery with Class 8 transport, and what the disappearance of the human driver would mean for the 3 million Americans who call the cab their home. We will look at the physical internet and how transport vehicles will eventually move with the same seamless efficiency as data packets on a fiber optic cable. This is the conclusion of our deep dive, where the machine, the human, and the future finally collide. Don't miss the final chapter of the American transport story. The concept of the physical internet is no longer a theoretical white paper in 2026. It is the operational reality for Alex and his fleet. Imagine Alex sitting in a darkened command center in Indianapolis, his walls covered in real-time telemetry from a fleet that is no longer just composed of trucks, but of sentient nodes in a massive self-optimizing network. This is the final destination of the transport vehicle, the transition from a driver-controlled machine to an autonomous modular system. To understand this, we must look at the Level 4 autonomous trucks currently running the I-10 corridor from Phoenix to Dallas. These vehicles are equipped with a redundant array of 8 LiDAR sensors, 12 high-definition cameras, and ultrasonic arrays that create a 360-degree safety bubble that updates every 50 milliseconds. In 2026, these trucks operate on a hub-to-hub model. A human driver like Sarah handles the complex, unpredictable urban environment from the warehouse to a specialized transfer hub located just off the interstate. There, the trailer is hooked to an autonomous tractor that handles the long, monotonous highway miles without the need for sleep, food, or breaks. This shift has redefined the very structure of the American transport vehicle. Because these autonomous tractors do not require a human occupant for the highway leg, the cab is being redesigned. We are seeing the emergence of cabless tractors, sleek, aerodynamic power units that are essentially engines and sensors on wheels. Without the weight of the sleeper berth, the glass windshield, and the life support systems for a human, these vehicles have significantly lower tare weights. Historical trends show that for every 1,000 pounds removed from the vehicle weight, fuel efficiency or battery range increases by approximately 1%. For Alex, the potential outcomes of deploying a fleet of cabless autonomous units include a 20% reduction in operating costs per mile, driven by increased uptime and decreased aerodynamic drag. But the transport vehicle of 2026 is also becoming a part of the physical internet through modularity. Imagine if the cargo was not just loaded into a trailer, but into standardized smart pods that could be seamlessly transferred between a truck, a train, and a massive cargo drone. These pods are equipped with their own IoT sensors that monitor temperature, vibration, and humidity. In this ecosystem, the transport vehicle is simply a carrier for the pod. When Sarah arrives at a regional distribution center, her truck doesn't just back into a dock. It releases a modular pod that is then picked up by a smaller, electric last-mile delivery vehicle. This eliminates the rehandling of goods, which is where the majority of damage and delay occurs in the modern supply chain. Case studies from early 2026 indicate that modular pod systems can reduce total transit time by 30% by bypassing traditional sorting facilities. We must also examine the last-mile evolution, where the transport vehicle becomes a mother ship. In 2026, Alex's delivery vans are equipped with roof-mounted drone bays. As the van moves through a suburban neighborhood in Ohio, the onboard computer identifies 3 packages that are destined for houses on a cul-de-sac. Instead of the driver stopping the vehicle, the roof opens and 3 autonomous drones launch, deliver the packages to the porches, and return to the moving van to swap batteries and pick up the next load. The transport vehicle in this scenario is no longer just a mover of goods. It is a mobile launchpad and a data hub. This integration of ground and air transport is the only way the American logistics system can keep up with the 2026 demand for 2-hour delivery windows without clogging every residential street with idling trucks. The infrastructure itself is evolving to meet these machines. In 2026, we are seeing the first pilot programs for inductive charging lanes on the I-80. This is charging while driving technology, where copper coils embedded beneath the asphalt transfer energy to a receiver plate on the bottom of the transport vehicle via an electromagnetic field. Imagine Sarah's electric rig traveling at 65 miles per hour and actually gaining battery percentage while climbing a grade. This solves the energy density problem we discussed earlier. If the road provides the power, the vehicle doesn't need to carry 15,000 pounds of batteries. This turns the American highway into a massive, continental-scale power strip, and the transport vehicle into an electric trolley that isn't tethered to a wire. However, we cannot ignore the human impact of this evolution. While the technology is breathtaking, the role of the driver is undergoing a profound transformation. Sarah is no longer just a trucker. She is a logistics technician and a remote operator. In the rare event that an autonomous truck encounters a situation it cannot resolve, such as a complex construction zone or a scene where a police officer is using hand signals, it doesn't just stop. It pings Sarah in a remote operations center. She puts on a VR headset and takes control of the vehicle via a high-speed 5G or 6G connection, navigating the obstacle from 1,000 miles away before handing control back to the AI. This teleoperation is the safety net of the 2026 transport network, ensuring that the movement of goods never ceases. The economic implications are equally massive. As transport vehicles become more efficient and autonomous, the cost of moving goods across the United States is projected to drop. Historically, transportation costs account for about 8 to 10% of the final price of any product you buy. If we can cut those costs in half through the technologies we have explored, aerodynamics, electric drivetrains, autonomous operation, and modular pods, the potential outcomes for the American consumer are significant. It means fresher food, cheaper goods, and a more resilient economy that can withstand global shocks. As we conclude this deep dive masterclass, let us look at the final definition. What is a transport vehicle? In 1926, it was a wooden frame truck with solid rubber tires. In 1976, it was a chrome-plated diesel giant. In 2026, it is a data-driven, zero-emission, autonomous node in a global physical internet. It is a machine that breathes air to stop, uses fire or electrons to move, and uses artificial intelligence to see. It is the most complex, regulated, and vital tool in the history of American commerce. Everything you see around you, the chair you are sitting in, the device you are watching this on, the food in your refrigerator, is there because a transport vehicle did its job. We have deconstructed the engine, analyzed the tires, navigated the legal web, and peeked into the future of autonomous movement. You now understand the invisible giant that keeps the heart of America beating. But while we have mastered the world of land-based transport, there is another frontier that is undergoing a revolution just as radical. The trucks move the goods to the ports, but what happens when those goods hit the water? The scale of the machines that move 90% of the world's trade makes a Class 8 truck look like a toy. If you thought 80,000 pounds was heavy, wait until you see the engineering required to move 200,000 tons across the Pacific Ocean on a single ship. How do these massive vessels survive 40-foot waves? And what happens when the global shipping lanes are blocked? The world of maritime transport is our next great frontier. We are moving from the highway to the high seas. Are you ready to see the monsters that truly move the world? The journey into the global shipping wars begins in our next masterclass. Stay tuned because the scale is about to get much, much bigger.